All right, so the Fourier series was what we're going to talk about. The other day, I kind of talked through a couple of different things. In this particular section of the class, I'm going to focus really on two sections in the book, 9.1 and 9.2. All right. The 9.1 is a long section. There's a lot of stuff in there about what we're going to learn about is the three forms of the Fourier series. We're going to introduce all three of them. There's a lot of equations. I don't know. There's probably like 100 and some odd equations in that section of the book. I don't really use them. I try to simplify those a lot, which is what we started to do the other day. All right. My basic sense is there's three forms of this thing, but you kind of only need to know one, and then you can kind of translate back and forth to the other. Then 9.2 talks about some common signals. So common signals would be things like things we see a lot. So it's going to be sinusoidal signals, square waves, sawtooth waves, things that happen pretty commonly in electronic systems. Okay. All right. So we give sine waves kind of a special treatment, I guess, in circuits. Your sophomore year, in a lot of ways, is about sine waves, right? You're seeing this. Well, if you're in circuits 1, you haven't seen it yet, but you see it in this class. You're going to see a lot of treatment of sine waves in circuits 2 when you get there, right? What's so special about putting a sine wave into a circuit like this? If you're in circuits 2, what's special about this? What's special about this as opposed to other types of waveforms? So in circuits 1, circuits 1 is a boring thing. What do you have? You have always your voltage sources, your current sources are always DC, meaning they're always constant. They don't change. Okay. Circuits 2, they can change. So even in circuits 1, when you have differential equations, you still have constant inputs, right? You have constant voltage sources, constant current sources, and then you just have the capacitor voltages basically reaching a steady state, or the inductor currents reaching a steady state of some kind. If I have a sine wave going into a circuit, you guys know, even if you haven't taken circuits 2, you know at this point there's a differential equation that comes out of that. And that differential equation is the transient response and a steady state response. If you're in circuits 2, I guess one of the key things, why we spend so much time on sine waves is why. Any idea why do we spend so much time on sine waves? Well, I've said a lot of signals include them, right? So a lot of audio, power, and things like that, I have sine waves. But there's also the case that with sine waves, I can simplify a lot of stuff. Right? What can I simplify down to if I had that circuit here, an RC, and I had that voltage source? What's that? What'd you say? Yeah. Oh, who said? Somebody said something. Well, I can convert the sine wave to a complex exponential, right? That ultimately allows me to use what in circuits 2? In circuits 2, what tool are you using if you're in that class? Phasors. You're using impedance analysis, right? You can use the phasor analysis, and I think of it usually as impedance analysis, right? I can think of these things. I can think of a capacitor not with a I equals C dV dt, but I can think of it as a capacitor has an impedance 1 over j omega c, right? Or an inductor has an impedance j omega L, and I can just do circuits 1 all over again. What's the catch to that? To use impedance analysis, if you're in circuits 2, what's the catch? I can't use it all the time, right? Impedance analysis only works under 2 conditions. What are the 2 conditions? What do all my signals have to be to use impedance analysis? Okay. That's your Have to be what? Phases. Those be in phase. They have to be sine wave. It only works for sine wave. They can even be different frequencies. I can find a way to do it with different frequencies. I have to have sine waves, and I can only be analyzing for steady state. Right? Those are the 2 catches, right? And it comes from the fact that if I gave you the differential equation for this thing, and the differential equation would be, in this case, it would be V out equals, this would be Vn equals RC dV out by dt plus V out. All right. If you guys were to, if I looked at this and I said to you, okay, well, this was my steady state input, you would guess that my output is V out, cosine, same frequency T plus some phase shift. You represent that by a phasor. You use the complex exponential, and essentially this equation, if I go through that whole approach where I said, okay, well, I guess a particular solution that looks like this, and I convert that over to the complex exponential domain, this equation becomes the same equation that you do when you do impedance analysis. I don't know that you notice that, right? But that's actually what it is. If you actually did the impedance analysis to say, okay, I got a voltage divider to get V out from V in, the equation that you would get doing that is the exact same equation you get by guessing this, going to the phasor domain, plugging that all in here, right? You get the exact same equation from it, right? So basically in impedance analysis, we just say, well, screw it. We don't need to actually use the differential equation. We can just use the fact that anytime I have a d by dt, it just simply becomes j omega when I have sine waves. And that's what gives rise to impedance analysis. All right. So sine waves are there's a simple way to analyze stuff. What happens if I give you this? Let's say I put this waveform, it's periodic. What do I have to do with this? Can I use impedance analysis with this? I cannot, right? Because this is not a sine wave. All right, what is this? With this, technically, I have to do differential equations. It's like I apply a constant, and then I apply a constant that's 0, and then the same constant again. I have to basically to do differential equations over and over again to figure out what's going to happen. Or what I can do is I can say this thing is actually a sum of sine waves, and I can do impedance analysis at each of the individual frequencies. All right, so it basically allows us to simplify a lot of stuff. All right. So I gave, this example the other day. I said, if I'm taking a solar panel, which is a DC output, and I put it into this device called an inverter, this V sub I looks like this guy right here. This is the grid that I connected to right there. That waveform that looks real choppy, that's a periodic waveform, right? And I can analyze that and I can figure out what sine waves are inside of it. And it allows me to simplify a lot of the analysis that I do. All right, so we're kind of explore that. I gave the example the other day too. This is the voltage in epoch. So this is a real measurement of what that voltage looks like. And I said it has a lot of quote unquote harmonics. Right, so I kind of used that term loosely the other day, harmonics. What did I say a harmonic was? So this guy I'm saying he's got 60 hertz as his base frequency, what we're going to define as his fundamental frequency. And then he has 120, 180 hertz, 240 hertz, 300 hertz. How are all those frequencies related to each other? 60, 120, 180, 240, 300. They're all multiples. They're all multiples of the fundamental. The fundamental being 60, right? The fundamental I can see because, okay, it goes through a zero cross here, reaches another zero cross there. That's 16.7 milliseconds. That's 60 hertz, right? This guy also has 120, 180, 240, 300. What would the next one be? 360, right? So we're going to learn more about those. We call those harmonically related when they're integer multiples like that. All right. You don't typically have things like a 1.5 times the base frequency. Typically, they're integer multiples. All right. So to go through this, we need to make sure that we're comfortable with the different ways of thinking about the sine wave. And that's what I started doing the other day. I'm just going to quickly kind of repeat that and then kind of get into my Fourier stuff. So I basically said I got 4 different ways of representing a sine wave. The first would be, and so this form right here, where I say C cosine omega t plus phi n. That's the way that you do it actually all the time in circuits, right? Circuits 2, you do it that way. Why do you do it that way in circuits 2? And you guys use phasors. I know that you basically you learn it this way, and then you very quickly go to phasors, and then you stay there. Why? What's always true about having cosines in a circuit? Or really, what's true about having cosines in a differential equation? Because that's That's what we're dealing with here. If cosine is my input to a differential equation, what's true about the output of my differential equation in steady state? Always. It's okay. I heard a couple of real values. All right, so if I have a cosine input, what's always true about my output in steady state? Also cosine. What's true about a frequency? Same. The frequency input, frequency output is always the same. There's only two things that can change when a signal goes through a differential equation. What are the amplitude and the phase? All right. So basically, this form is really useful here because it tracks amplitude and it tracks phase. All right. Now, what ends up being nice is ultimately because of all the simplifications that we showed, if I use that form number 4, and I plug this into the differential equation, I'll solve for C and the angle. And then I can just go back to that form knowing that I have this relationship between the real part of that and whatever that is up there. The fact that those things are related to each other allows me to greatly simplify the analysis. Argument I always make is it's weird to use complex numbers. I get it. It seems strange. You're using imaginary numbers. You learned that in high school. It seemed weird because we're talking about numbers that are imaginary. But it captures basically a phase shift and an amplitude change in a way that allows you to use the algebra that you're learning in circuits 1 without having to do all the calculus that would go with handling this very common input here, cosine omega t in a circuit. All right, so it simplifies an analytical process for us a lot. That's why we spend so much time on it. All right, so we have basically 4 ways of thinking of that thing. So that's probably my most common form because I think of it in terms of what does a system, meaning typically what does a circuit do to an input that's sinusoidal? Well, it shifts it, that's the phase shift, and it makes it bigger or smaller, that's the amplitude change. If I have a cosine with a phase shift, I can think of that as the sum of a cosine and a sine at the same frequency. All right, so there's a certain amount of A and B that are required to make this waveform. All right, and there's a process for figuring out what that A and B are, right? It's also true that this same waveform up here can be thought of using Euler's identity as this. This is Euler's identity. I think of this as basically 2 rotating vectors in the complex plane. All right, which one of these vectors rotates clockwise and which one rotates counterclockwise? So this is a vector. This is a vector. Which one rotates clockwise? The right one, the negative. This one's clockwise, the one that has the negative frequency, right? Because the angle is going to be getting more negative as time advances. So more negative would mean going this way, right? So that would be clockwise. If it's getting more positive as I go that way, that would be counterclockwise. All right, so this one is the counterclockwise, that's the clockwise. This one here, we say, again, if I used Euler's identity and I expanded C e to the j phi n, e to the j omega t, just to make sure we're on the same page, when I say expand that and take the real part, what would I do if I quote unquote expanded this thing? I don't think I can delete that. How would I, when I say expand this using Euler's identity, what would I do? So real part of C, and I'll write it this way, e to the j omega t plus phi n. Expand that using Euler's identity for me. C times what? C cosine omega t plus phi n. That's one part of it. Plus what? Plus j times the amplitude sine omega t plus phi n. So I'm saying the real part of that thing is the cosine part, right? So it all comes back to that thing at the top. All right, so both of those use Euler's identity, both approach 3 and approach 4, just in different ways. All right, so approach number 1, I basically say I got this guy right here. All right, so as I've drawn this right here, this particular sine wave, what's the phi value here? What's the phi for this picture? 0. For this one, it would be 0. Why? Because this guy looks like cosine. Could also be 360 degrees, I guess, right? If I shifted it a whole period, you wouldn't notice, right? Or I could shift it 2 periods, you wouldn't notice that either, right? So we would just say phi equals 0. Now here, all right, I've got 4 cosine omega t minus 90 degrees. What else does this look like it is? Let's look at this. Also looks like a sine wave, right? All right, so one of the things I can see with this is, I can always make a relationship between cosine and sine. There's relatively easy ways for me to do that. And oftentimes we make use of this form as well, where I say, all right, I didn't want to go through this process of deriving this the other day, but I used trig identities and I said, well, if I have the cosine of omega t plus phi, that's basically like I've got the sum of 2 angles. There's a trig identity for that. And I can basically convert that into this equivalent statement down here. And so I basically have these terms right here. So I have c cosine phi cosine omega t minus c sine phi sine omega t. What that means is, what I'm figuring out in this form is how much of a cosine do I need to add with how much of a sine at the same frequency to get to that. And so I figured that out using the trig identity. So the value of A is this c cosine phi, and B is minus c sine phi. All right, so what we did the other day is I said, okay, well, here's a case where I've got 2 or 3 different waveforms, right? So let's look at this. Which one, looking at the picture that I've drawn here, I got 3 waveforms drawn. Which one is the x of t? And which one is the cosine and which one is the sine? Let's start with the easy. So 0, t equals 0 is here. This time I got the full string. So this is t equals 0. Which one's the cosine and which one's the sine? The yellow is the sine, and the red is the cosine, right? So this guy is the cosine term. And the yellow is the sine term. So that means the blue must be x of t, which is this 2 cosine 2 pi 1000 t plus 45 degrees. All right, so I think of this as A cosine. What frequency should I put in here? Not A cosine omega t. Let me get, what's the specific number I should put in there for the frequency? What's my omega? 2 pi 1000, right? You should know that. What's up, man? This guy, you mean? It doesn't. So this is the thing. So x of t, good question. I'm glad you're asking. I have to clarify. So x of t is the blue one. That's not at its peak at t equal to 0. Right? His peak is actually up at 2. His amplitude is 2. Right? It just so happens that the cosine and the x of t are actually kind of crossing over each other at t equals 0.
How you're saying the cosine wasn't there.
Yeah, well, so it's confusing, right? So what I'm doing is I'm saying that cosine omega t plus phi is equal to a cosine omega t with no phase shift plus a sine omega t with no phase shift. That the additive combination of those 2 things is going to give me 2 cosine omega t plus 45 degrees.
Thank you.
Yes. So when I write this, all right, what should I write here? So I'm going to say cosine 2 pi 1000 t, and I'm done. Right? There's no phase shift in there, right? And then plus b sine omega t. All right, what I want to figure out is what's the A and what's the B? What are the amplitudes that I need to get to be able to create this summation? All right, now before I do that, one thing real quick. What is the frequency of this in hertz? Make sure that we're clear on that. 1 kilohertz, right? Just to be clear, 1 kilohertz, right? All right, so 1000 hertz. 1000 is the frequency of this guy. All right, so how do I figure out A and B? Well, I just said if I know the frequency here, I can say A is always equal to C cosine of phi, and B is always equal to negative c sine of phi. Well, in this case, what is c and what is phi? C is 2. And what's phi? 45. So I say c cosine 45 degrees. Cosine of 45 is 1 over square root of 2. This guy becomes 2 over root 2, which is approximately 1.4. If I do that here, so I say negative 2 sine of 45 degrees, this works out to be about the same, about negative 1.4. And so I can kind of see that that's right here, what I get for the cosine, right? How can I tell that its amplitude is about 1.4? Yeah, so this is 1.5 right here. So this is 1.4. So that looks correct. And then for the sine wave, I see that it's negative because sine is supposed to start at t equal to 0, it's supposed to start going up, right? This guy actually starts going down, hence the negative, right? And I can see that his amplitude is about 1.4 as well, because if I look here, looks like he's about the same size as the cosine, and he's there. Now, I chose 45 degrees as that phase shift. If the phase shift was 30 degrees, either the cosine or the sine, one or the other would be bigger, right? It all depends on the phase angle. By choosing 45 degrees, the sine and cosine have the same amplitude. They're not always, right? If I chose a different angle, they would have a different amplitude, all right? Now, this is kind of where we ended the other day. I said, all right, well, what happens, all right, if I use the third approach, which is the Euler's identity approach? And I say, I think of this thing as two rotating vectors. So what I sort of said the other day is I said, this guy here is this vector. He's rotating in the counterclockwise or positive direction. This guy right here is rotating in the clockwise or negative direction. All right. Now, the thing about this, I know this always kind of confuses people to look at it this way, but I think of this as if I have c e to the j phi n over 2, basically it's like I have c angle phi n over 2, which, you know, I can write that way. And so that's another way of writing this. And I can say this guy is c over 2 angle negative phi n right there. Okay. What I do is I say that means I just define this guy here as alpha, right? So alpha is this. I call that alpha 1, and I call this alpha minus 1. Now, why I call it 1 and minus 1, why is that? Well, for reasons we're going to see a little bit later as we go through the class today, but I call it 1 and minus 1 because I think of the frequency here as this guy is moving with the frequency omega. This guy is moving with the frequency minus omega. When I get into Fourier series here in a minute, I'm going to talk about things moving at 2 omega and minus 2 omega, or 3 omega and minus 3 omega. And so that number that I'm multiplying omega by becomes important to me. Okay. All right. So at what time have I drawn these two vectors? T equal to what? Because these vectors are rotating, right? This guy is, as time moves, this guy is moving. At what time have I actually drawn these two vectors here? 0. Because I'm saying this angle here is phi n, okay? And this is my complex plane, right? So this is the real part. This is the imaginary part, like that. All right. So let's say I had this guy here. Same thing we did before. 2 cosine 2 pi 1000 t plus 45 degrees. All right, so the way I write this is I say, all right, if you don't remember, you go back to this sort of summary here. So what do I have? I say, that means I can write this thing as this. Okay, so let's do that. I can write this thing as alpha 1 e to the j omega t plus alpha minus 1 e to the minus j omega t. All right, and from what we said there, alpha was equal to, if we look on the previous slide, what was alpha? Alpha was c over 2 angle phi n. And then alpha minus 1, we said was its conjugate. So how would I write the conjugate? If I know that alpha one is C over two angle phi n, how do I write the conjugate of that? Yeah, what do I change? Is the magnitude any different? Is the magnitude of a conjugate any different? No, it's just the same. What do I do for the angle? The angle is the negative. So I say negative phi n like that. All right. So really all I'm trying to do here is kind of pattern match to this thing, right? It's fairly straightforward, right? So what do I put for omega? Let's do that first. What do I put for omega in both of these things? 2 pi 1000, right? So I would say alpha 1 e to the j 2 pi 1000 t plus alpha minus 1 e to the negative j 2 pi 1000 t, like that. Okay. All right. Then what do I do for alpha 1? What would alpha 1 be? If this is my x of t here, and this is my relationship for alpha 1, what would I put there? 2 over 2. Well, no, so I'm saying alpha 1 is, is this complex number. Angle phi n. What's my angle I would use here? 45. Right, so it's 1 angle 45 degrees. What's my alpha minus 1? 1 angle negative 45 degrees. Okay, so here's my complex plane. And I drew these unit circles here. Let's say this is 1 and 2, right? Circle with the radius 1 and radius 2. Where would I put alpha 1? Where would I draw alpha 1? 1 angle 45 degrees. Where would it end? So it starts here, right? Where does it end? At the first circle, right? And he's got an angle up of 45 degrees. This guy would be alpha 1. Alpha minus 1 is its conjugate. Right? This angle here is 45. This angle here is negative 45 degrees because he's going down. Okay? And this is what it looks like at t equal to 0. As time advances, those two vectors would rotate. Okay? So that's the third approach. The fourth approach is to say that it's the real part of basically this dynamic phasor idea, right? So if I do that in this particular case, this guy was 2 cosine 2 pi 1000 t plus 45 degrees. So what would I sketch in this case? Well, I want to sketch this guy. So I want to say this is the real part of what? What would I write inside here using this relationship for this waveform? The real part of what? 2 e to the j phi n, so e to the j 45 degrees, times e to the j what? 2 pi 1000 t. All right, so for this, if this is my plane, I say this is the real and imaginary. This is 1, this is 2. Where would I draw this at t equal to 0? So I'd start here. And where would that guy go? First quadrant, yeah, and where would he end? At this circle or at the circle with a radius of 2? Circle with a radius of 2. Right? So it's going to come out like this. This guy is 2 angle 45 degrees. Right? Or 2 e to the j 45 degrees. Like that. Okay. Two different ways of writing that same equivalent thing. The important thing is if I once I know of waveform, there's going to be a lot of things I'm going to ask you to do on the homework to go through a number of these problems, right? if I have a waveform in one of the forms, I can shift it back and forth to the others using Euler's identity or trig identities or whatever. I have ways to go back and forth. All right, when we do the Fourier series, we basically have three forms of the series, which we're going to get into now. There's the sine, cosine, shifted cosine, complex series. There's three ways of doing it. They're entirely equivalent to each other. They all have their own nuances and differences and annoyances, right? The most annoying to a lot of people is probably this one, because it's got complex numbers, right? This one's really hard to do calculus with. This one's really easy to do calculus with, but it's complex numbers, right? So that's what makes it ugly, right? So what we have, and I'm going to use this a lot, right, is I've got a set of relationships that exist for a single sine wave. I can look at this and I can see basically the relationships. If I know the amplitude of the original cosine is C, I can figure out that this alpha 1 and alpha minus 1, I can figure out that these magnitudes are related to the C values. The A and the B values are related to each other. And I also see that there's a special relationship for the phi here, as well as the C and the way that's related to the A and the B here. All right. It's not, you can figure those things out fairly easily. We needed to. All right. I'm going to rely on kind of going back to those things as much as we can as we go through our analysis. All right. So everything I just did was for a single sine wave. You need to understand that. You're going to have on the homework next week, a bunch of those things to look at. But what I really need to start looking at is this notion of the Fourier series itself. So I need to go basically to situations where I got multiple sine waves. So I talked about this the other day, right? So any periodic waveform can be thought of as a linear combination of periodic basis functions. That's a big fancy way of saying basically I can add up a bunch of harmonically related sine waves and create that waveform. Okay, I can create that square wave. Now this particular guy here is periodic. First of all, when I say a linear combination, all right, one thing that probably screws people up, if I say a linear combination, that ultimately means that I'm going to use this symbol, right? What is that symbol? It's a sigma, it's a summation, right? I'm going to have series, right? So we're going to basically, when I say a linear combination, it means that I can add a bunch of terms up to create that, okay? All right, so we're going to go back to probably remembering that terminology of series where I have that kind of summation notation. All right, so I say that this guy is periodic. What's the period of this thing? And what's our definition of periodic, first of all? We've mostly looked at sine wave. What's the definition of being periodic? Time it takes to oscillate is a period, right? So basically the time it takes for the waveform to repeat. So I say what the period capital T solves this equation. Where is the value of the function now? Where does it repeat? The time T is the amount of time it takes for it to repeat. Okay, that is a key thing for us. All right, because we're going to start looking at waveforms like this and have to figure it out. All right, and it's not going to be as obvious as it is with a sine wave. All right, so I want to visualize the Fourier series for a second, right? Because basically what I'm saying is it's a linear combination of sines and cosines. So one way of writing this is that this periodic waveform, let's call this guy x of t. One way of writing this is that he is equal to some, I'm going to say some constant. What should I call it? I'm going to call it x0 for right now, some constant plus basically a summation from n equal 1 to infinity of an cosine n omega naught t plus bn sine n omega naught t. Right? That's what this thing is. Okay. Now, it's going to take a little bit of time to probably think through that expression, right? But if I told you expand that series, all right, what would you do? How would you expand this series? Okay, so x0 plus, help me expand that series. I plug in n equal 1 first, right? If I plug in n equal 1, what do I get? Well, I get a1 cosine what? Omega naught t plus b1, yep, sine omega naught t. Right? That's one term. What's the next one? A2 cosine 2 times omega naught t plus b2 sine omega naught t. Oh, 2 omega naught t. Yep, that's a 2. And then effectively, this keeps going on up to infinity. All right. Now, the job in Fourier analysis is usually to figure out what is A2 and B2 and A3 and B3. Right? In other words, I'm trying to figure out, quote unquote, in my mind, I think of this as, I think of it, the AN values and the BN values as knobs, right? They kind of adjust how much second harmonics, so how much of this guy do I need and how much of this guy do I need to make the original waveform. All right, so what I want to do is, first of all, make sure, I know for a lot of people, getting your mind around that sigma notation, right, is not straightforward. So I want to look at that, but I want to visualize this thing for a second to make sure we understand what's going on. I took a square wave over one period. All right. What I did here was I took first of all, what is that? Is that a sine or a cosine? That's a sine. All right. I put a sine inside of that thing. So that's the same frequency. So it's aligned with it in time. All right. And what's the period here? 1 second. Okay. So what's the frequency omega for that thing? 1 hertz. So what's the frequency omega? 2 pi. I call that omega naught. Right? I'm going to call that the fundamental frequency. Right? That's the basic frequency that is inside of this thing. And if I looked at this guy, what I can see, so we're going to look at this. If I wanted to, I think I have it eventually. Hang on. I don't know where I put it. I'll make sure I put this in the notes that I post. You can draw this thing with the square function in MATLAB, but I think I'll get to it in a second. The square function in MATLAB can draw that square wave. All right. And I'll lay that out here in a second. That aligns with it, but not quite perfectly, right? So if I looked at this thing, what I would say is if this is my original x of t, this guy that I have right here, what's his amplitude? Well, I can't quite tell. His amplitude's a little bit bigger than 1, not quite 1.5. If I did my analysis, what I would find is that the amplitude of that waveform is 4 over pi. Not obvious, but that's what it is. All right. If you do the calculations, that's what it works out to. Is that red waveform? Is that a sine or a cosine? Sine. So that's 4 sine 2 pi t. Now I see that it's aligned up in time with the square wave, but they're not quite the same. So what happens if I add a DC value to this thing? So when I say a DC value, let's make sure we're clear on that. What frequency is DC? 0. Something that never changes has a frequency of 0 hertz. We call that DC because it's constant, right? So when you have DC circuits, you have constant voltage sources, you have constant current sources. So we call 0 frequency DC. Okay. So if I want to start adding up waveforms to get closer to that square wave, how much DC do you think I want to add to it? Any idea? Yeah. So in other words, how much constant would I want to add to this thing to get, so how much would I want to add to this sine wave to get it closer to that? That's a good guess. It turns out that I want to add about 1 volt. All right. There's a reason. There's a logic to it. There's a way to calculate it, right? So I add 1 volt. If I add 1 volt, then basically I see that he sits on top like that. So in this case, now what I'm showing is I have 1 plus 4 over pi sine 2 pi t, right? And I see that now the two waveforms, they're lined up with each other height-wise, and they're lined up with each other timing-wise. Now, the cool thing about this in particular is that what's happening is that they're lining up with each other. How much cosine do I have here? Do I have any cosine? No, it's just a sine wave, all right? Now, what have I done here? Well, that waveform looks a little bit closer, right? So if I look at what I've done, I started out with a sine wave that had the same time alignment. Then I shifted it up so that they were kind of lining on top of each other. Now they're getting closer to each other. What did I do as I went from, so here I took a sine wave. Then I shifted the sine wave up. What did I do here? Do you think? Well, I still have 1 plus 4 over pi sine omega t. What do you think I added to it? Not a cosine wave. It's a good guess. It looks to me like, when I look at this, it looks like there's maybe some higher frequency stuff happening. Why say higher frequency? Why do I say that? Well, because I see more ripples in one period, right? Something that's higher frequency is going to vary more times in one period, right? So it looks like I've got some other term in here. In reality, what I have is the third harmonic. So I have, and again, it's amplitude. There's a way to figure it out, but it's 4 over 3 pi. So when I say the third harmonic, that would be sine 3 times 2 pi t. Like that. Okay. Then I added in the fifth harmonic. And I got this. So this is 1 plus 4 over pi sine 2 pi t. And I added 4 over 3 pi. Again, there's no obvious reason why you would know that the amplitude should be 4 over 3 pi. That's the stuff we learn how to calculate, right? I just kind of want to introduce the concept here. Then I added fifth harmonic. What do you think I write for the fifth harmonic? 4 over 5 pi. And I would say sine of 5 times 2 pi t. Okay. Now, here, I think I went up to the 99th harmonic. All right. In other words, I'm including terms in here that go all the way up to 99 times 2 pi. Now, if you notice that, what's going on? Well, now that summation is looking pretty close to the actual square wave. Now, he's got these little Batman ears that are kind of developing, right? And they're really hard to get rid of. There's a name for this. You have to, basically, the Fourier series is infinite. I would have to add in infinitely many harmonics that ever truly get up to the square wave. Okay. So this behavior, we're not going to talk about it much. Something called Gibbs phenomenon. That's one of those words I can't spell. Right? We're not going to talk about that much, but in reality, what happens is that's being caused by high frequencies that usually in any real system kind of get filtered out because they're very high in nature. So what I did as I went through that process, I didn't calculate this, but what I did was I basically laid out for you how much of each of the terms here needed to be added in to create or to approximate this waveform. All right. And the approximation gets better and better. So if I added in only the base frequency, it had the same timing. If I added in the DC, it got closer. If I added in the third harmonic, it got closer. If I added in the fifth harmonic, it got closer. If I went all the way to 99, it got even closer still. Right. So what I did was I basically was applying the right amount of each of those terms to get this guy to look closer to what it should. The job of us really is to figure out what is the amount of each of those waveforms that needs to be added in. So I was using this form. There's 3 forms of the series. All right. And so these are the 3 forms of the series. I have this sine cosine version, shifted cosine version, and the complex version. All right. This one is the one that we're going to do most of our analysis with because it's a heck of a lot easier to do the calculus with that last one, with the complex form of the series. All right. It's very annoying to do it with these guys. Now let's take a look. for the first ones here, I see that I go from n equal 1 to infinity. For this one here, I go from n equal negative infinity to infinity. Why would this guy take twice as many frequencies as the other two? Why does the complex form take twice as many as the other? In other words, this guy goes from negative infinity to infinity. He goes from 1 equal to infinity. Basically, he needs 2 times as many values. Why?
Is it because you need so many others?
Yeah, they got a positive frequency.
Yeah, it's gonna be possible.
And a negative frequency. Yeah, they combine to create the cosine. That's exactly it. Right? So I'll need 2 of these. The good thing is if I know the positives, the negatives, the coefficients here are just the conjugates. So I only have to do half the work to get the same answer, right? It worked out to be okay. All right. Now, one thing that's going to bother people is this DC term. It always causes some problems. We'll get to that. All right. So let's get to our core definitions. I've been using these terms, but I want to make sure they're defined. So basically, I have the fundamental frequency. All right. The fundamental frequency is, like in the case of what I just did there, fundamental frequency was 2 pi. Right? The base period was 1 second. The angular frequency that goes with that is 2 pi. Right? So the fundamental period frequency is the largest period of the waveform, or the smallest frequency. All right. The largest period, right? Frequency is 1 over the period. Right? So the largest frequency, the largest period, smallest frequency. All right. I talked about this thing, harmonic number, n. That's the integer we're talking about. So I'll refer to, and I have been, the first harmonic, the second harmonic, the third harmonic, whatever, right? So those harmonics are always n times f naught. All right. So when I say when n equal 1, I'm talking about the first harmonic, or more commonly, what we call this is the fundamental frequency, the fundamental term. Because it has the basic frequency of the waveform, the fundamental frequency that everything's built from. N equal 2, I call the second harmonic. And then so on and so forth. The 0 order harmonic we call the DC or average term. All right, so we have n equals 0 for that. Okay, so we call that usually we call it the DC or the average, because if you look at what I did here, like when I added 1 to this, when I say it's the average, where did I get that? Well, because that 1 volt there is the average of x of t. That's how I figured that out. I calculated the average. So what's the definition of an average? If I say I have a waveform x of t, how do I calculate? So often I write the average in these brackets like this. Well, so in discrete time, when I've got sampled stuff, that would be, how I would do it, right? If I told you in calculus, how do I get the average of a periodic waveform? How do I get that? You guys remember how to get the average of a periodic waveform? So it's basically do the summation, right? So like you just said, sum up over the points, but the summation in continuous time would be the sum over a period divided by that period. Now, in reality, I'm going to say it like this. Usually you do it from t to t plus capital T, right? So I don't have to do it from 0 to the end of the period. Sometimes it'll be easier for me to go from like negative t over 2 to t over 2. If I'm smart about it, sometimes my calculus gets easier. All right. So I usually keep it open-ended like that. I just have to integrate it over any period. To me, I look at it and I try to figure out which period is going to be easiest for me to integrate over. Okay. All right. So the whole idea for me is when I look at this thing, I think of it like this. I think of it as saying, okay, well, when I look at the waveform, I can make the waveform be the summation of, so I call these here my basis functions, the term we use a lot, right? So basis function, meaning if I think of like the 2D plane, you can make any vector in the 2D plane using some combination of x hat and y hat. Right? You learned in physics, right? You play with vectors. I can make any vector by adding some amount of x hat and some amount of y hat. So I think of x hat and y hat as sort of the basics. They're the things that define the 2D plane for me. What I'm looking at here is I'm saying the world of functions, periodic functions, can be thought of as basically different summations of essentially a constant. So a constant plus cosine omega naught t, so sine omega naught t. And then how can you tell that these two here are the second harmonic? Looking at these two pictures right there, how can you tell that they're the second harmonic? The frequency, which one has a frequency that's higher? Is it these two or the two above it? These two have a higher frequency, right? How can I tell that? Well, they repeat, and if I look at it, this waveform, these two waveforms repeat twice in the amount of time that it takes the one above it to repeat once. Right? That's the idea of a frequency. A higher frequency waveform is going to repeat more times in the same amount of time. Right? How fast are these guys repeating? 3 times, right? So if I look at the top one, so if I look at this one, and I look at this one, both of those are cosines, right? So from here to here, all right, this guy repeats once. This guy repeats 1, 2, 3 times. That's the third harmonic, right? So what I do is I think of, okay, well, I take those original basis functions, quote unquote, right? And what I do is I say, how much do I need, what number do I need to multiply this guy by to get closer to that? How much do I need to multiply this guy to get closer to that? So on the basis of what I just did there, this guy needed to be 0. This guy needed to be 4 over pi. This guy needed to be 0. That guy needed to be 0. This guy needed to be 0. And this needed to be 4 over 3 pi. Now, let's just unpack that for a minute. In other words, to get to the square wave that I drew, that's how much I needed to multiply each of these guys by to get closer to that original waveform. Right? That's what I did as I walked through those pictures. But just understand that for a second. I just said A1 equals 0. Why did I say that? This guy equals 0. Why did I say that? Well, if you went through the process that we just did, right? This was the process. I said, all right, there's the square wave. I said, I need some amount of sine wave, and I need some amount of DC, and I need some amount of a third harmonic sine wave, and some amount of a fifth harmonic sine wave, and some amount of a bunch of sine waves that got me all the way up to here. So, did I ever use a cosine? I never used a cosine in that process. Now, again, it's not obvious why. I mean, no one would just guess that probably off the top of their head, right? There's a way of calculating that, and we're going to get to that. But I can see that A1 is equal to 0. Why is A1 equal to 0? Because I don't want any cosine. It doesn't take any amount of cosine to build that waveform. And that's why A1 is 0. It makes sure that this term doesn't appear in the series. So the thing I want to make sure you guys understand too is this here, that equation is what I am using to create this red waveform, right? And I'm just including a different amount, okay? So we'll look at some code to do that later, right? But basically, I'm just, what did I do? I wrote a for loop, basically. And I had my for loop. I can't have my for loop go from 1 to infinity, right? You'd be waiting until the end of time for the for loop to finish, right? So what I did was I had my for loop go to 1, and then I had to go to 3, and then I had to go to 5, then I had to go to 99. Right? So I was basically just implementing this equation with a for loop. Okay. All right. So why are A2 and B2 equal to 0? Why are A2 and B2 equal to 0? I didn't have any second harmonic. All right. If you look at that, I went straight from, so I had first harmonic, I had DC, and then I went straight to the third. And then I went straight to the fifth. Now, again, you wouldn't necessarily know to skip 2 and 4. You can do calculus, which we're going to do in a second to figure out. But we're not going to do it today. We're going to do it next week. The calculus to figure out how much A2 and how much B2. But if you went through the calculus to do that, you would find that those numbers would be equal to 0, right? Harrisburg, North Carolina is calling them. All right. That makes sense. All right. Stupid Zoom. All right. So let's go through an example like you're going to have on the homework. So here's a waveform that is a Fourier series. This guy's S of t is a Fourier series here. How do I know it's a Fourier series? Well, it's a bunch of sine waves that are added together. That's a Fourier series. Now, are they harmonically related? I guess we don't know that yet. So I'm telling you that it is. All right. Let's look at this. So I asked a couple of questions, very similar to what you'll have in the homework. So determine the fundamental period, capital T, which should be the smallest possible period over which the function repeats. Okay. And then determine n sub d, which is the number of the highest harmonic frequency. So if the signal has 10 harmonic frequencies, n sub d is 10. All right. Now, I gave you 10 as an example. I don't necessarily know what it is. All right. We'll have to find out. All right. Let's see. Okay. So here's the waveform. If you plot that guy. All right. First of all, is he periodic? It looks ugly. But he is periodic. Okay. If I asked you to find me the period, so the definition of periodic we said was, where does the value now repeat? So capital T is the amount of time it takes for the function to repeat itself. So looking at this, any ideas? I know how I would do that. How would you do it? I see repeating happening. In particular, if I look at the value right here, it repeats again after some amount of time, doesn't it? Where? Yeah. So yes, this guy is in milliseconds. So T would be equal to 4 milliseconds. Yeah, 3 milliseconds. Minus 1 milliseconds. Right? So the value here to the value there, meaning that this guy has a period of 4 milliseconds. So fundamental frequency in hertz, what is that? Because nobody ever talks about, even though we write cosine omega t, we never talk about frequencies in omega. You don't go to Duke and somebody says the frequency on the grid is 377 radians per second, right? What does it say? It says 60 hertz. Okay? You don't say that your clock, your computer is a 2 pi gigaradians per second, right? You say it's 1 gigahertz, right? So we use frequencies in hertz most of the time. So what do I have here? So the frequency of this, what would that be in hertz? How do I calculate that from the period? How do I get that from the period? So 1 over t. So 1 over 4 milliseconds. If I do that calculation, I end up with 250 hertz when I do that calc. Okay, 250 hertz. Okay, that's the fundamental frequency. So, all right, now there's another way to do this, and I want to be clear, right? One other way to do it, I like to do it that way where I can visualize it. The other way you can do it, the book talks about this in that section 9.1, is I can use something called the greatest common divisor, or the GCD. That's something you learned, I don't know, 5th grade or something like that, and probably it may be held somewhere in ROM, but it's probably gone in your head, right? The greatest common divisor between basically 1,000, 1,750, and 1,500. If I did that calculation, this would work out to be 250 hertz. All right. So I would get the same result if I ran that comment or that command. Okay. All right. Now looking at this guy here. All right. So we just said the fundamental frequency is 250 hertz. So what frequencies do I have in this waveform? All right. What frequencies do I have in this waveform? So the fundamental frequency is 250 hertz. What frequencies do I have? Well, the easiest way for me to do this probably would say, I'm going to make a little table here. I'm going to say, let's start with different values of n, and then let's calculate what we've got. So this is what n, and I'm going to say n times f naught over here. What value of n should I start with? What's the lowest? It should be obvious here. Look, what's the lowest frequency I have in this? 0. So what value of n would that be? 0. I got n equals 0. That's DC. Do I have that in this waveform? The answer is yes. The 10, right? There's a 0 frequency term, meaning a constant term that's there. All right, so n equal 1 would be 1 times 250. Do I have any of that in this? So this guy does not. How about this? How about these guys? Are either of them 250 hertz? No. So I don't have that. Second harmonic. What would the second harmonic be? 500. Yep. 2 times 250. Do I have any of that? No. Third harmonic. That would be what? 750. Do I have any of that? No. Fourth harmonic. What's that? 1,000. Do I have any of that? Sure do. Okay. All right. So now let's see. I've got the 0 and the 1,000 covered. If I keep going with this, I have, let's see. So 5 would be what? 1,250. Don't have that. 6, 7. Let's see. So 6 would be 1,500. Do I have that? I do. All right. Seventh harmonic would be 1,750. And I also have that. Okay. Do I have anything beyond that? Nope. This guy has up to 7 harmonics. So if I was saying what's the highest, this ND in this case would be 7. All right, 7's the highest number that I've got. All right, now looking at this form of the series, I can figure out, well, how much A and B do I have at each of those terms? Okay. All right, so first of all, we just said that we look back at the previous slide, we said we have a DC term. We don't have a fundamental, don't have a second harmonic, don't have a third. We do have a fourth, don't have a fifth. We do have a sixth, and we do have a seventh. Okay. So let's start out with number 4 here. All right, so at the fourth harmonic, we have 50 cosine 2 pi 1,000 t. So pattern matching with this expression, do we have any sign at 1,000 hertz? No. So that means the B sub 4 is 0. Right? But I do have an A sub 4, don't I? What would A sub 4 be? Looking at this waveform. So this is the value. That's the cosine that I have at the fourth harmonic. What would A sub 4, this amplitude, be? 50. Like that. All right, that would be 50. Now, what's the next guy I have? Going up in frequency, 1,500. At 1,500, I have a sine term, but not a cosine. So again, pattern matching with this formula. How much A do I have at that frequency? So how much A do I have at 1,500? 0. All right. How much B do I have at 1,500? 2. Now at 1,750, my seventh harmonic, how much A do I have? 0, because again, I got a sine term here, right? And then how much B term do I have? 20. And then everything else, I don't have anything of. So they're all 0. Okay. Because I needed to multiply whatever the base cosine and sine were at those frequencies by 0 to make them disappear. But they don't exist in that way. Now I do have a DC term though. I have a 0 frequency term. All right. So what do I put for that? Well, there is never a B term at DC. Okay. Now looking at this, it's annoying. It says A0 over 2. All right, you guys aren't going to like that. There's a reason why they do that, to align it with the complex series. All right, what is the DC term here? It's 10. So pattern matching with the thing below it, I'm saying 10 equals what? So if I try to match the pattern between the one above and the one below, 10 equals A0 over 2. So for A0, what would I put? 20. That's going to annoy you later. Right. I know this is where it annoys, kind of annoys me too, but it does that because of what the way the complex series does it. Okay. If you think about it, at any given frequency in the complex series, you're getting half of the amplitude of the total cosine. So to align that, they do this. Let me not say anything further because I'm not sure it'll just burst your brains, and you don't need to. Just remember that relationship. All right, now, if I were doing this in MATLAB, this is how I would, in MATLAB, I'll ask you probably, give me a vector that goes from A0 to the highest harmonic that I have, right? So I did AN and BN, look how I did it, right? For n equals 0 up to n equals 7, I put in those values here in the order that they appear, from 0 all the way up to 7. It's the kind of thing I'm going to ask you to do in the homework, right? Is to enter them into a vector like that. Now, what happens? This we'll probably have to pick up on next Tuesday. But let's say I wanted to ask you to go to another version of the series, right? So I just did the version of the series that looks like this: sine and cosine. Let's say I want to go to essentially that form, this guy right here. Well, I have a set of formulas that we did to relate the A and B values to the angle and to the amplitude. So if I go through those things, I can use these formulas to kind of shift back and forth between them, right? So we're gonna do that example in some more detail. But I look at what I did here, and I'll go through this code again on Thursday or Tuesday. Yeah. But basically, if I know the A's and the B's, I can relate them to the C's and the Phi's, and I can relate the C's and the Phi's to the Alpha. I can relate the series to each other. All right. Now, we're going to eventually get ourselves to not just pattern matching, but I want to be able to look at I want to be able to give it a function, and I want to be able to do the calculus to actually figure out what these values are, which we'll do next week. That is it.